my emphasis or interest has often been in weak signal, narrowband, VHF, and microwave. And like soon after I got my first license, my novice license in '61, I was building tube transferters and getting on 2-meter sideband and doing things like that. And I moved into microwave, and I don't actually operate and transmit, at least first person, that much. And these days, I transmit a lot, but it's digital. But my interest has been technical, probably more than emergency or social or some of the other things that ham radio has to offer. And in that vein, in the last few years, probably the last 15, I've moved back down from microwave and moon bounce and things like that into HF territory, some of the more traditional stuff, and digital modes, narrowband, and some of these modes. And about 15 years ago, I started looking at typical residential environments like I lived in with an HOA, and found, like probably the majority of hams in the US have found, that noise levels are really high. And you say, well, what's that? And the usual answer is, oh, it's all that digital stuff. And so I set out to see, well, what can we do? And what's it really take to be good? So let me start by trying to share a screen here. If this will work. Hang on just a second. And it says host disabled participant screen sharing. So I'm going to have to wait for a screen to share. Can we do that?
We'll get that.
Go? Let me know when I should.
You should be good now.
I think we're there.
Yep, you should be good.
Okay, great. Are you seeing a screen?
We sure do.
How's that look?
Yes, we are.
Okay, excellent. I've got only about 20 slides, but there's probably too much material here. And some of it maybe seem controversial. There's links and things. I'm not going to go in depth on it all. And I think maybe just in the interest of not, I don't want to encroach on the next section. I refer you to the links that are embedded. And all this slide set is actually available on the webpage here at the bottom, right there. That will get you at the top of my webpage is a link to this set of slides. If you want to mail me, I hope that's correct. Yep, you got that right. You can mail me, and of course, be glad to talk to you and go into any of the too many things that are here. So. What I want to do is basically, I'm coming at this idea of HOA antennas, not from, you could go legally and say, what can I make them do? I'm going to put up a 200-foot tower. I'm being a little non-confrontational, I suppose. And in that vein, stealth and small are kind of like a good territory to be in. And I want to start off by some theory. I'll try not to bore you too much. As I say, I'll probably go too fast and not dig down too far. But I'm going to say some things that will seem a little maybe surprising to a lot of you relative to antenna theory. I want to go on and talk a little bit about difference between receive and transmit. They're not the same, and the same solutions, the same antennas, the same problems do not exist in both. They're different, and recognizing that really does help one when you're constrained to a homeowners association or a neighbor or something where you've got to be you're restricted. I'll follow the technical part with some antennas that have worked well and can work well in an HOA kind of an environment. Actually, the couple I'll show you aren't anything but HOA constrained, but they could just as well be there. And I want to really emphasize, this is not a silver bullet. We've seen a lot of antenna types in the previous segments of this, and really helpful to get ideas for what to do. But I want to say that this is not a panacea. Each situation is unique in all kinds of ways. Your kind of restriction, you might be in a townhouse or apartment. You may have more or less room. You may have there's all kinds of things. So this is not a recipe for do this and everything will be fine. I want to start off with an idea of size and what small means. And in this slide, which has got a whole bunch of stuff, there's really two axes. if you look on the left side, I'm saying physical size, as you go that way, it gets bigger. And kind of in the middle here is a small backyard, whatever small means to you. So physically, really small antennas are down here at the bottom, along the bottom, and physically large antennas at the top. And in the horizontal axis, I'll have electrical size, where the size of the antenna structure is small relative to the middle ground. Here is a half-wave dipole. I just picked these arbitrarily. So you've got little tiny things over on this side, and you've got really big things like, mile-long beverages, or maybe EME arrays that are filling 2 backyards. But you see that there's four quadrants here. You can have small in one domain and big in the other, or you can have small in both or big in both. And I've just put in some rough ideas of what I mean. So when we're thinking about small, it depends on what wavelength we're talking about, because obviously down here, at 2,200 meters, everything is small. None of us has, I think none of us has, thousands of feet of room for an antenna. And, you can be all these combinations. So I want to say something about that will be a bit surprising about small antennas. And that is, for an antenna that's small, and I'm saying half wave or smaller, it doesn't matter how big it is. And that sounds like a crazy statement, but I want to emphasize that this part right here, the matched, and that some of you may have already discovered that if you've played with antenna modelers like NEC2, you might have accidentally put in the wrong frequency or the wrong size and discovered that when you get an answer that's kind of the same. The problem, of course, is they are different, but from a point of view of how much signal they capture, what their pattern is, what their capture area, their pattern, they're the same, essentially the same, within a half a dB. If you want justification for this, there is physics justification. You can go to this link. But essentially, if you look at considering these fundamentals, you find out that over here, the transmit and receive, if it's a half wave and smaller, essentially all the same gain. It sounds really funny. It's like, well, how can that be? Doesn't a bigger antenna capture more? And the answer is no, it doesn't. And of course, then the next question is, well, why the heck don't we all use tiny antennas and be done with it? And the answer is there is a difficulty. The difficulty is not the size of the antenna, but it's matching to the radiation resistance. And radiation resistance is something that you may have heard of. It's not what you measure when you put a VNA or a SOAR bridge. Oh, hang on, let me back up here. Or a SOAR bridge on your system. It's got to do with the physical size of the antenna, and maybe nothing at all like what you measure with a impedance meter that you might use. The interesting thing about it, I mean, if you may be familiar with this model, if you have for example, if you're on a 160 meter mobile with an 8-foot whip, you have you've got a big loading coil that tunes out the equivalent series capacitance and leaves you with this radiation resistance, which is really where the power, if you're transmitting, that's effectively it's a mythical resistor in a sense. That is, it isn't really out there, but it's the value that the radiated power appears to emanate from. That is, you have to have that your transmitter power coupled to that resistance. And on receive, it's the reverse of that. All the signal coming in appears to come from a resistor that is getting really small as the antenna gets electrically short. So I can't overemphasize what you measure is not the radiation resistance. Well, it may be for a half-wave dipole, it can be very close, but for short antennas, generally it's not. This model over here, I don't know if you're seeing my cursor or not, is a model of a half-wave dipole from Fornac 2. And you can kind of see the antenna here. It's this black thing. Oh, I keep doing the wrong thing here. It's this black thing on the edge that has no field in it, because the actual conductor, which is this vertical length here, doesn't have any field. What this plot is showing is the longitudinal electric field. And you see these hot spots at the ends of the antenna, and in the case of a half-wave dipole, a little bit at the center. It's these components that contribute to signal in DX, or far field. And I'll talk about far field, near field in a little bit. But as you get really close to an antenna, things are kind of strange. But as you get far away, the only thing that's left is called far field radiation. And the element itself, the thing we see and call an antenna, isn't really radiating. The radiation occurs in this region of space here at the tips, and on some antennas, longer antennas, you get a contribution here, which for more details, as I say, follow the link. But I got two things here that might kind of bother you, and that is that all short antennas essentially work the same, except for this match problem, and that the elements aren't radiating. So well, I'll leave that for now, but there's some links if you want to follow what the physics of that is. And this, I think, matters as we look at small HOA antennas. So I want to now move to the difference between receive and transmit antennas. What a receive antenna system is trying to do, it's just trying to hear, believe it or not, DX noise. And you say, well, I don't want to hear noise, I want to hear signal. Well, from a view of propagated fields of things that are propagated from DX or far field, the signal and the noise are, you define one as signal because that's what you want to hear, it's, communication, but they're at a ratio. There's some strength of field, and that's what you're trying to get to. And so what you want your receive antenna to do is to deliver that to your receiver so you can do as good a job as possible for that DX signal. And obviously you're not going to improve on the signal noise ratio that's coming in from DX, but you sure can hurt it. And some ways that we commonly hurt it are listed here. I don't want to go into a whole bunch of detail. I do want to say one thing about coax, though. This is another alarming thing. Most of us feel like if we hook a coax onto an antenna and we hear noise, well, it must be coming in from the antenna. And it's very important to understand that coaxial line is only shielded for differential signals. It doesn't shield when there's common mode. And that means if you don't have good balance, you can put a coax line on and actually it becomes the antenna. And we do things, we put on broadband balance, but compared to the need, these are often not nearly enough. On transmit, rather than just trying to get to a low noise floor, compared, a propagated noise, we're trying to get all the transmitter power we can into this sorry, I didn't do that very well, the radiation resistance. We're trying, because that's what radiates in the far field, and so the guy can hear you. And so we're trying to match to a radiation resistance as opposed to achieve a low noise floor. Really different needs. You can put numbers on this, and first looking at receive. On receive, this plot, there's a lot of stuff here, and I'm not going to go into detail on it, but this is a propagated noise plot by ITU, measured over a lot of seasons and places in the world. And it's, again, it's got several curves here. If you look down here, there's a C, a man-made noise quiet receiving site. That's kind of like a goal. If you can hear as well as somebody in a nice quiet rural site, well, that's, you're there. And generally speaking, that's this C curve right here. I mean, it's got a minimum. Sometimes it might, well, especially I hear it at 1 megahertz. So the axis here going this way is here, the ham band 630, 80, 40, 10, and then 100 megahertz up here. So we're looking, kind of in this region of the chart. So in order to hear that DX noise, it's got the signal in it, that is your goal, you've got to have a receive system that kind of has, isn't contributing to noise. You can't have local ingress from any kind of, for any reason, that is increasing the noise you know, if your receiver is up here, you're not going to hear the signal and noise you're trying to down here. It'll just look like, oh my gosh, the band's dead. So your goal is to have a receive antenna system, the whole thing. You're trying to match to that SNR, that signal to noise ratio that's in the radiation resistance of whatever antenna you've got, and deliver it to your detector, to your receiver. On this side over here is what the S meter would be, an S9 minus 73, it should say DVM. And you can see S corresponding S. So if you're here on 40 meters, about here, and you're trying to get to propagated noise, well, you better have a receiver system. When you hook to a matched antenna, a dipole or something, you're well matched to the radiation resistance, you better not see noise that's higher than that. And so much of the time, perhaps at 40 we get away with it, but much of the time for many stations, that's not the case. And consequently, they are not hearing as well as they might. The green curve here shows the problem with going to a small antenna, the HOA antenna. If you drop the antenna size down to a 1/10, going from a half to a 1/10, 5-to-1 change. So at 40 meters, that's a 13-foot wire. At 80 meters, it's a 25-foot wire, so forth. If you do that, that radiation resistance is dropping. And if you don't do something to match to it, if you just tune out with a loading coil, tune out that series capacitance that it looks like, and hook your 50 ohm, so that was not what I meant to do, and hook your 50 ohm system, your transmitter receiver to it, you are down 15 dB from the get-go. That is to say, the stuff you're trying to see suddenly got weak, which is what most people observe. They put a small antenna on and say, well, gee, it's not as loud as a big antenna. Well, the problem isn't the signal to noise, just we're not properly matched to it. But if you're matched to it, then of course you can be up here, you have that same thing. But matching becomes a problem. And that's really shows up on transmit. On transmit, if you're trying to match say 50 ohm system to a 1 ohm radiation resistance, you've got a problem that you have that's a big Q. You've got to have an antenna tuner. We use those, but in the end, it's impossible with components and materials known to man to match perfectly. And the Q and bandwidth gets very narrow. This is what we saw on the loops and things like that, is they get very narrow bandwidth because the Q is so high trying to match to them on transmit. So large antennas are nice. Dipoles and resonant antennas are nice because they're resistive. And a dipole, it's 75 ohms out there. It's pretty easy to get a 50 ohm transmitter matched to. So larger antennas are nicer in that respect. They're nicer because they have lower fields, and those fields mean lower environment losses. You don't have so much absorption by nearby clutter. Heights can usually help. It gets you away from stuff. It gets you up. There's actually can be an increase in signal to noise ratio. A high antenna may have a takeoff angle improvement, and there may be some reasons. But here again, we're talking about difference between a matched antenna and an antenna on receive that simply gets us to the signal to noise ratio. But there's a trick. Kind of, it's not really a trick for receive antennas. And that is, since we don't actually have to match to the thing, all we really need to do is to deliver the signal to noise ratio that's on that little antenna, it's too small, and deliver that to the system. And the trick there is, if we use real high impedance preamps, not a 50 ohm preamp, but something that doesn't load down that little small antenna, we can actually deliver the SNR, the signal and the noise. It's an active device. It's an amplifier in it. We can deliver that to a low impedance system. And there's a dual of this. If we're talking about loops instead of dipoles, you usually use it with instead of using a high impedance preamp, use a low impedance preamp. But you probably already have one of these if you think about it. You saw it on the chart I had earlier. These things right here, car radio antennas, are really small electrically. I mean, we're talking 300 meter band, 1 megahertz or something. And here we have an antenna that's inches. That's really physically and electrically small. But it turns out that a high impedance preamp on that delivers enough signal that you can drive down the road and listen to 560 kilohertz AM broadcast from a long way, and you hear propagated noise, and everybody's happy. So moving on to small and invisible antennas. What we're saying here on transmit, when we go to these small antennas, built into them because of that the high Q are large fields, and that small resistor, the small radiation resistance that we're trying to match to. As an example, at 630 meters, that's our second bottom band, our medium wave band below broadcast band. A 60-foot vertical, which we might think of as being electrically big at some wavelengths, is small, and its radiation resistance is really tiny. It's it's down sub-tenth of an ohm. And when you try to hook that, if you typically you have a 60-foot vertical and you drive it as a whip, you put a big old series inductor to tune out the capacitance. When you do that, the ground side though is in series with whatever the ground can produce. And typically, even with pretty good radio systems, 20 or 30 ohms, maybe slightly less than that, it's in series. So you've got this big glossy resistor in series with this tiny one that you're trying to get power into. And guess what that does? That means you got big efficiency loss. You can put 100 watts of transmit power into the system. It's matched. It looks like 50 ohms, but in that 0.1 ohm, only 300 milliwatts gets radiated. And the good news is, at those long wavelengths, that actually can get you several continents from Colorado. On receive, there's a different problem. Because the R is small, you have low signal voltage, and other things can get in the way and dominate and make it so you can't hear as well as you might. Here's some things that help you do it. Here again, I mentioned that coax is not really a shield for common mode. And you may stick the coax, hook the coax and antenna up, see the noise go up, and what you're really hearing is noise coming in on the feed line or by another way. There's a couple of other ways, and I do reference that in one of the links here so that you can get an idea. Okay, enough of that. I've talked, boring you with technical stuff for maybe too long. Let me talk a little bit about some practical things that have worked. And I've divided, here's the original chart that I was showing with physical size going out vertically and horizontal size, electrical size going horizontally. Green are antennas that are good for receive, or I'm talking about for receive. And red, where we have to match it, are for transmit. And of course, you can use them on receive, but this matching problem gets so severe that, what we found is that the probe solution has not only easier to make it work, but it has the advantage I didn't highlight. This is broadband. It works everywhere. It isn't limited to a very narrow band that the high Q match situation is. So I want to talk about some things that have worked here, and starting that, I've used a dipole, an active dipole. Here it is at the bottom. Which is actually a dual of a small broadband mag loop, not the kind of mag loop that you got to tune and is high Q, but one with a low impedance preamp. So an antenna like that can serve, before you get on the air with your selection, an antenna like that can serve a really good purpose. And that purpose is to map your location. Now, not everybody's going to have freedom to move an antenna, or to move an antenna. If you're in an apartment, you may be lucky if you can get outside. But if you have freedom, it turns out that the noise, these unwanted noise sources, are almost at HF. They're almost always what's called near field, and near field and far field are different. And a near field noise source has a characteristic that it drops with distance much faster than the truly radiated far field that we're familiar with. The inverse square law you may have heard. If you double the distance, the signal drops by 6 dB. Well, on a near field noise source, and that's the kind that HF sources often, especially long wave ones, generate, if you double the distance, you might go a quarter of a quarter of a quarter. So you can drop really fast, which means there's some benefit for mapping your location if you have the freedom and finding a quiet spot, quiet polarization, using one of these small, here at the top here, there's a dipole. It's horizontal. I probably would run it vertical, actually. I didn't want it in my face for the picture. But you can, this is a completely portable active antenna system. There's a Kiwi SDR in the backpack and a battery, a Wi-Fi link to my phone. And so I can sit there and I can look at the whole spectrum as I walk around the yard or around the location. I can map it for near field noise and figure out how to get away from stuff. And a lot of times, a few steps even can make a big difference. I show here a dipole. You could also use a magnetic loop. As I say, it's kind of the dual of a dipole. And there's a link here. This link is to an LZ1AQ one you can purchase. I'm here using one I built. But the thing that saves the day for near fields is you can get away from it sometimes. Now, if you have a little flexibility, and it may not take as much as you thought. In the next part, I want to show you the results of what my yard looked like. Here is in the middle of the day, looking from 0 meg, there's audio down there. Here's 10 meters up here. So this is a plot from the Kiwi. I automated it so it would measure every few hundred kilohertz. And I'm measuring what the noise is. These big spikes, by the way, are shortwave broadcast or signals where I happen to land on an actual signal and I wasn't measuring noise. So ignore the man behind the curtain. These spikes here are just signal, and that doesn't count. But you can see here that the noise itself is kind of like you can see a general shape to it, more or less. And the interesting thing is here's the 4 areas in the yard I measured: north, southwest, southeast. And I could walk around and do that, but there's some difference. It's clear that I'm better off. Well, I keep doing that. I'm better off with southwest yard, orange down here, than I am with southeast. And so there's a hint. This is vertically polarized. It's very possible I could do some polarization thing. Now, the next thing is next slide shows the same kind of thing, but instead of walking around my yard, what I'm doing is walking around my region. And this plot shows 3 plots. The yellow one is kind of an average of my yard for comparison. I've taken out some of the shortwave stuff here. You can see the gaps. But the orange one is only maybe 3,000 feet southeast of my house. And I live in a HOA community. And this is just outside the edge of the community. It's not even a diameter of the community away. You can see these levels. Look at this. It's dropping at least 10 dB. And if I go to this place right here called QP, that stands for quiet place. That's Fossil Creek Reservoir, about 2 miles east of me. And it's really quiet. This blue plot right here is the noise measured midday from 0 to 30, fixed at Fossil Creek. And by the way, that's as quiet as anything, even the remote site I'll talk about in a minute, that's as quiet as anything around. At this site, measurements we've made show that it is as good a receive situation as you can basically get in this part of Colorado. So not that the state is bad, but just for comparative sites. Let me go to the practical antennas for this. I've been talking so far about HF. Let me just throw a bone to UHF, because that is one of my favorites. And I built an antenna that is a matched antenna, so it works for both receive and transmit. And it's also broadband. It'll go from 100 megahertz to 2 gigahertz. And I built it in 3 sizes here. There's different low end is really the only difference. You can see them here. The bigger one goes down, almost doesn't hit 6 meters. It's 4 meters, but not 6. And so you can see this is a biconical. The interesting thing here is I printed it on a 3D printer. That plastic is a thing you can print. It's not Home Depot. It's Harbor Freight TIG rod, and it's basically it's just a dipole. But just a dipole is a good thing because it can be decently matched. And it can work broadband, unlike a single band dipole. Here's one semi-stealth at my house, hidden in the trees. You can see it there. It's actually this antenna stuck in the trees. And so there's an example of a VHF stealth broadband solution. It'll work on 2, 432, 900, 1296, all our ham bands. On HF, I do have an antenna which you can question whether it's truly stealth or not. This is my weather station, which the important part here, as you can see, the mast is holding it up, which is certainly visible. But if you look at it and you see the weather station here on the top, maybe I get by. What you don't see is, maybe you see the extension, but there's a piece of number 28 wire, actually 2 pieces that I could, one go, it's a 20-meter dipole, or if I short it here and feed it from the bottom, it's a 40-meter dipole resonant, or I can actually put a loading coil down here, a big garbage can with turns on it, and I can run this thing on 630 meters. And with that even the few hundred milliwatts of radiated power I actually get, I can do multiple continents. I've gotten into Europe and South America on 630 meters with my weather station. So I want to make a point too, that antenna does not have to be resonant, because it really, when we're talking about it, this wire, the stuff we see is the radiator is up here in space. All this other stuff we see and put up is really matching network. So going on to finally, a system that has worked very well and has been in use is a hybrid. And I want to talk about, there's 2 portions to it. There's a loop on ground, which we've also earlier presentation showed some examples of. And that one covers upper HF. And then over here, I have a 2-meter dipole, active dipole, like the one I showed in the picture of me walking around the yard, that I used from basically audio to mid HF. And they have appropriate preamps, a very high impedance preamp right there, and a 50 ohm preamp but with some matching. There's a 9-to-1 transformer right here coming off the loop. And they get combined, they come down from Cat 5. And this antenna, hybrid antenna system, has been in use up at the club location that Greg in Zero EMP's place at 7,500 feet. And using it it's a receive-only system, but using it to spot whisper, it's very near the top of North American receive rankings. It does very well. The noise floor is low, and it's the nice thing about it is, and you think about it, this thing's in the ground, this loop on ground, as previous sessions showed, you can make it so nobody can see that one. You can bury it an inch if you want. And this thing's pretty small. It's, it's not obvious, and even an apartment probably could stand it. I would say try it out. When I wrote this slide, I said try it out here, but I got to put an asterisk right there, because right now it's off the air for the first time in about 3 years for maintenance at Greg's house, and it'll hopefully be back on. But when it was on when I did this slide, you can see in 24 hours, here's what it heard. Bands are down here. So 10 meters to actually no 2,200 meter spots. It's summer. But 630 meters through 10 meters, and there's 7 continents there. There's a DP0 German outfit in Antarctica. Every continent, 24 hours, one system. It really works well. Since that has gone off the air, we have just put online another one that's essentially identical, but this one is located at 80 degrees north. It's VY0 ERC. It's part of a Canadian environmental study, Polar Environmental and Atmospheric Research Lab. You can go to the website and see. You can see this is a summer daytime picture. There's no snow or ice, but it gets that, but it really gets wind. But the reason I threw this picture in was, if you look here in the foreground, you can see the loop on ground. It's just a diamond, and I don't think, that didn't work. Well, right there is the preamp. And over here, there's over right there is an active dipole. So the two antennas I showed in the previous slide, there's some Cat 5 going up to the red building where there's two Kiwi receivers, which are on the internet. And that's where these spots come from. This thing is spotting like crazy. It's still got a noise problem. We're working to improve that ingress that I talked about. There's other noise sources you don't want, but it's really doing very well. And of course, it's in a quiet location with no HOA, but it would work for an HOA. It's low profile. So in some situations, this kind of an approach, and again, remember, this is not a silver bullet for everybody. Mapping's involved, figuring out what you need are really are part of the solution. And it's almost a career figuring this stuff out. So finally, I would just summarize, if you're interested in working on it, and it really is an effort and it takes a long time to find out and peel out all the things, I would say work on receive first. It's very possible that you're being heard and don't know it. That is, that a better station in the world hears you and you just didn't even know it. If we look at whisper spots, for example, a very small percentage of stations are good in that they hear far better than the mass. So if you can get your receive system down, you may discover that ham radio is really different. And I list some orders of things to consider. Common void, things that are hurting your system. The pro broadband antenna approach has a lot of merit in a small HOA kind of environment. Figure out what your environment's like and optimize your antenna solutions, receive and transmit. Well, transmit doesn't care about noise, but receive does. And what most people do is they say, when they see noise, they say, oh, it's my fill in the blank, LCD TV, my plasma, my this or that. And they go try to play whack-a-mole with noise sources. It's far better to remove the way the signals get in than to try to whack-a-mole and solve them, because you may not even find them all. For transmit, it's about how to get power into radiation resistance. It's not the SWR bridge. What you measure with the SWR bridge may be primarily, depending on what your system is, may be mostly ground or something other than the antenna, the place, this radiation resistance, which is contributing to your working DX. So, and finally, I just say, if you're interested in pursuing it, even with restrictions, I think most stations stand a good chance of being able to greatly improve their situation and have a lot more fun on ham radio. And with that, Joe, we can go on to the next section. And if there's questions, we can maybe stick them all in at the end, because I don't want to run our time out.
This presentation was brought to you by the Northern Colorado Amateur Radio Club. For more information, visit our website, ncarc.net. Thanks for watching, and don't forget to like and subscribe.